Okay, second video of 13.6. We're finding area of parametric surfaces, or at least doing calculus on these parametric surfaces first. So the first task is to be able to compute the tangent plane to a surface S given by or traced out by a vector function r of uv with parameters u and v. And that would be at a point p naught on the surface S with u naught, v naught being the argument of r to give us the point x naught, y naught, z naught, which is p naught. So remember that what's happening is we're taking a region in the plane that includes points u comma v, and we're mapping that region, that planar region, into a three-dimensional space, and we're getting this sheet-like object that we're calling a surface. Okay, so instead of being flat and living in the plane, now it could have some bends in it or some curvature. So that's our parametric equations here for this surface. Now, if we want to find the plane tangent to a point on one of these surfaces, we're going to need the partial derivative of the vector function r with respect to v. We're going to need it with respect to u. Okay, at the point u naught, v naught. So in practice, this will be, each of these vectors will be numerically known. We'll have numbers u naught, v naught for our point p naught, and we'll be able to evaluate all of these functions after we take the partial derivatives of each with respect to the variable v and then the variable u in the second line there. So when we know that, what we've got then is if we're imagining a surface in three-dimensional space, so I'll draw it with some kind of curvature to it. We've got some point P naught on it. We want to find a plane that's tangent to it, sort of rigid, fixed plane tangent to that point on the surface. Well, we're going to need two vectors to find the normal vector to this tangent plane. So zooming in to have a look, if we have a vector in the u direction, say this way, partial derivative of r with respect to u, that's the derivative in the direction of u, and then the derivative in the direction of v. And then we cross ru and rv, we'll get a vector that is perpendicular, orthogonal to both of those vectors, sticking up out of the plane here, and that'll be our normal vector n. And that normal vector, the cross product of ru and rv, will be the equation of the plane. Now, what we've done already, though, is we've realized that to parametrize a plane, so if we wanted to give, we could give this vector in two different ways. It could be the linear combination of ru, rv at the point p naught. Remember, p naught is this point, the initial point for these two vectors. We could write it that way, or we could also write it with our standard normal vector n and the equation of a plane back in chapter 10 or whatever previous vector geometry chapter that came from. So that's our task. That's why we want r sub u and r sub v, the partial derivatives of the vector function in each of those directions. And that'll fully determine a tangent plane to any given curve. So, so long as that normal vector is non-zero, that cross product is non-zero, then we'll call S smooth, and we'll always be able to find a tangent plane to that surface S. Okay, so in our example we're given, we're asked to find the tangent plane to the surface with parametric equations x equals v cubed, y equals u cubed, and z equals 2u plus v at the point 8, negative 1, 0. So all the parts we expected are given to us. We write r as a vector function, x, y, and z as functions of u and v. First thing we need is r, the partial derivative with respect to u of r. Doing that in each component yields this vector function, r sub u. And then the partial of r with respect to v, same thing. This function with respect to v in each component, partial with respect to v, and this is what we arrive at here. And we note that the values u equals -1 and v equals 2, this takes some inspection. We look at this point and we look at each of these and we try to determine what u and v must be equal to for this point to come about. Right? We can't just pick any point. It's got to be on this surface. And in fact, if this problem gave us a point that didn't have u's and v's that satisfied this, it wouldn't work. We wouldn't be able to come up with a tangent plane because that point wouldn't actually even be on the surface. We would not have values of u and v that would give us this output for r. But in this case, u equals -1 and v equals 2. The reader can check that when we plug that into this vector function, we get this point. So these are the points we want to use. This is u naught and v naught, -1 and 2 respectively. When we plug -1 and 2 into this vector function, we get this vector. Similarly, we do that for r sub v. Now we want the cross product of these two vectors. That'll give us this normal vector n, so ru cross rv, and that's cross product taking place here, and we get out a normal vector of this. We'll use our old formula for the equation of a plane, and we have our normal vector times r, which is x, y, z, the variables, minus r naught, which is our point, -8, 1, 0. And we dot those two vectors together, and what we arrive at in the end is this equation of that plane. Now again, if we wanted to do this in a slightly more clever way, we could remember that in one of the previous examples in the previous video, we could have taken this as the vector A, this as the vector B. Oh, not that, sorry. This as the vector A and this as the vector B. Those would both be in this given plane, and take linear combinations of these. So maybe for the sake of something different, t times this variable plus s times, sorry, t times that vector plus s times the second vector, where t and s can take on any real numbers. And we add to that the point 8, -1, 0. It would look just like what we did previously when we had two vectors that needed to be in the plane, which ru and rv are in fact in the plane, and include the point 8, -1, 0. So two ways to do that. We've gone a little bit of a longer way to give this standard old expression here, but it depends on what it is you might be using that tangent plane for as to what form you should put it into. In this case, the choice was just arbitrary. Now, surface area, and this is sort of the main point of this section, is to calculate the area of one of these surfaces. So if we're given a surface S that's parameterized by some function R of parameters u and v, and u and v have some rectangular domain D in the UV plane, we'll just assume that its domain is rectangular for the purposes of this section to simplify our consideration and derivation of this formula. Well, we remember that we can divide this region D into subrectangles, R sub ij, using U sub I star, V sub j star to be the lower left corner of Rij for any of these subrectangles. And we'll take S sub ij to be the patch above R sub ij. So let's have a look down below in the drawing we've got. So here we've got a rectangle R sub ij with lower left-hand corner U sub I. That should actually be a V sub j in there. So let's make a note of that. So this is a V sub j right here. And above it, in three-dimensional space, out of this UV plane down below that maps to this surface, above it we've got this this patch right here. Okay, so that's the S sub ij patch for our surface. And what we want to be able to do is calculate the surface area of this entire surface for this given rectangular region below, or as it corresponds to the rectangular region below it. So in other words, this whole rectangular region is corresponding as the domain to the surface above it. In other words, the points UV that give us the points X, Y, Z above it. Okay, to that end, we need to be able to approximate the area of one of these patches. So what we've got so far is a trick that we used in the past. We know that R sub U is this vector approximately, right? It's approximately equal to the secant vector between these two. It's the partial derivative in the direction u. R sub v is similar. It's approximately equal to the secant vector along this patch. And the smaller these patches are and the smaller the subrectangles are, the more accurate that approximation is, until in the limit they're actually equal to each other. So, and we know that to find we can approximate the area then of this patch as the area of a parallelogram. And the area of a parallelogram would be this vector r sub u at ui star vi star cross r sub v at ui star vi star. And of course, really truly the secant of each of these lines is delta u times r sub u and delta v times r sub v. These delta u and delta v are constants, scalars, so they've been factored out of our cross product, just to make it look a little bit more like what the formula that we arrive at. So we see above in the exposition that the area of one of these patches is approximated by rectangles by the parallelogram that is has side length or vectors delta u, r sub u, and delta u, r sub v. Okay, and actually, again, v and r sub v. So working forward from here, we know that this would be the area approximately, and then we take the sum of all of these and the limit of the sum of these to do infinitely many of these patches and subrectangles, and what we arrive at in the end is that the area of this surface is, well, it's the limit of the double Riemann sum of expressions that look like this, and really that limit of the double Riemann sum becomes the double integral over the region D with respect to area. So let me make one more labeling down here. This is D, and this was our area S. Got to kind of connect it all together. So it's a really light derivation of this formula. And note that we also ensure the definition of r sub u and r sub v, but it's the same thing we were using for these vector partial derivatives in the tangent plane calculations. So let's use the formula. Find the surface area of a sphere of radius 2. So in order to use the formula we're given, we need to find a vector parametrization for the sphere of radius 2. Luckily, we know that from a previous problem earlier in these notes, and in the previous video we did that. So the sphere is parametrized by angles theta and phi, which range between these values. And for a radius 2 sphere, we just fix the amplitudes of these to be 2 in all cases. So there's our parametrization of the sphere. We need to find r theta cross r phi to plug it into our area formula. So first we find r theta and r phi, the partial derivatives with respect to theta and phi respectively. So there's theta, there's phi. We can check the details of that independently. Now we take the cross product of this vector and this vector, and that's this matrix determinant here. Quite a bit of work here, but we see some really nice cancellations come into play. In fact, this might even be written with some of those cancellations happening. The reader or viewer should double check that. But we arrive at an expression that looks like this. We simplify it even further in the next step. Here is our cross product written in a vector notation, vector form. And then we need to find the norm or the magnitude of that vector. So this is our calculation to find the magnitude. It's the square root of the first component squared plus second component squared plus third component squared. That's these three components, each squared summed up under the square root. Every one of those had a 4 or negative 4 in front of it squared. So that's a positive 16 under the radical, so 4 is factored out front. We continue to simplify this and we arrive at 4 sine of phi for this expression here. So with 4 sine of phi as our magnitude of the cross product of these two vectors, we can plug that function now into our integral over the region over the region D, which is the rectangle 0 to pi and 0 to 2 pi. We think about it in that sense, it can be seen as a rectangular integral since those are all just constants. And then our function for sine of phi, since it is a rectangular integral, we only need d phi d theta corresponding to 0 to pi and 0 to 2 pi. I know theta is involved, so it makes you think polar coordinates, but really if you look at 0 pi and 0 to 2 pi in a coordinate plane, it's just a rectangle from 0 to pi crossed with 0 to 2 pi. So it keeps this integral fairly straightforward to calculate. And in part that happens because all of this has been wrapped up into spherical coordinates. So all of our rotational stuff has already been taken care of in the way that this sphere has been parametrized. So evaluating this, we arrive at 16 pi. It's a straightforward double integral, the details of which are above. So the area of a sphere of radius 2 is 16 pi. The book actually does a problem like this, but with arbitrary area A, so it essentially derives a formula for this. So that's a nice thing to look at as well. So we would have derived the formula for the area of a sphere in general. Okay, so the surface area of the graph of a function. So if we are instead given a function z equals f of x, y, then we can think of x and y as their own parameters, and z being equal to this function of f of x, y. And that would be a parametrization of this function. It would be given as follows in vector form. Now, if we carry this out in terms of the formula on the previous page, r sub u cross r sub v, or r sub x cross r sub y in this case, take the magnitude of that, what we actually arrive at is this expression right here. Okay, the reader's encouraged to fill out those details, but it might be fairly easy to believe that r sub x cross r sub y magnitude is equal to everything that's in that that integral. So z sub x squared plus z sub y squared, just to shorten the notation. Of course, you should certainly confirm for yourself that that's the case, or at least see the details in the textbook about that. But what this does for us is, instead of having to go through all the work of finding the cross product of those two vectors, if we're given such a function z in terms of f of x and y, we can parametrize the graph of that surface as given here, and then, or think of it as that parameterization, and then just apply this double integral to come up with the area of that surface. So it's much more convenient. Some steps are cut out thanks to that, thanks to this little rule right here. So find the surface area of the part of the paraboloid y equals x squared plus z squared that lies within the cylinder x squared plus z squared equals 1. So this paraboloid within the cylinder of radius 1. Okay, and it looks like the cylinder is centered, has central axis, the y-axis. So we need to kind of change our formula a little bit. We want to write y as a function of x and z, and that's exactly suggested by this as well. So in this case, we've actually got x equals x, z equals z, and y equals f of x, z. So let me write that, or y equals y of x, z. So we'll say something like this. We have x equals x, z equals z, and then y is equal to f of xz. And really, it's just a permutation of names for things. We end up with a very similar formula, only now it's the function y with respect to x as a partial, and similarly for y with respect to z, partial derivative. Square both of those. Well, okay, first let's come up with these partials. Y sub x, partial of y with respect to x. Remember, we're looking here. That's going to be 2x. Same thing with respect to z, it's 2z. So we have 2x squared, 2z squared, both quantities squared, and we end up with 4x squared plus 4z squared. And now's a good time to realize that this region D is circular. Its projection onto the xz plane is circular with radius 1. So we go to polar coordinates. D is represented as a radius going from 0 to 1, and theta is an angle from 0 to 2 pi. So that'll fully establish our cylindrical region on the xz plane, or actually circular region, the projection of that cylinder onto the xz plane. And that gives us this integral, which really just requires a u substitution. Note that we are using cylindrical coordinates, so we do, polar coordinates, sorry. So we do need an r value in there, so per the formula. And well, that gives us exactly what we need for a u substitution on this term, changing our limits of integration, swapping out our differentials to match, carrying out the details in a pretty standard way. We arrive at this answer below. So just a little bit of a, standard looking, but still somewhat tricky to have learned in the first place integration with an application of double integrals. But there's nothing too difficult after we know the setup of such a problem. And really the key to that is to just follow this formula overall. So we should find that areas of these surfaces are actually kind of easy to calculate so long as we know or remember or have the formula available to us. So that should do it for section 13.6, parametric surfaces and their areas. In the next section, we'll talk about surface integrals. So now not only will we have a surface that we're looking at, we're going to think about a function on that surface. And so that'll be sort of an extension of the formula we see here, and we'll find that these formulas are actually special cases of those. So that'll be the next video.